Vinyl chloride. Vinyl chloride is an organochloride with the formula HCl. It is also called vinyl chloride monomer VCM or chlorophene. This colorless compound is an important industrial chemical chiefly used to produce the polymer polyvinyl chloride PVC. About 13 million tons are produced annually. VCM is among the top 20 largest petrochemicals, petroleum-derived chemicals in world production. The United States currently remains the largest VCM manufacturing region because of its low production cost position in chlorine and ethylene raw materials. China is also a large manufacturer and one of the largest consumers of VCM. Vinyl chloride is a gas with a sweet odor. It is highly toxic, flammable, and carcinogenic. It can be formed in the environment when soil organisms break down chlorinated solvents. Vinyl chloride that is released by industries or formed by the breakdown of other chlorinated chemicals can enter the air and drinking water supplies. Vinyl chloride is a common contaminant found near landfills. In the past, VCM was used as a refrigerant in its preferred IUPAC namethylchlorophenothird-namsvinyl chloride monomer malorophylline refrigerant or identifiers cause number 1,4-ide model ismal interactive imageable Stein referencer Chebikabia Chem Spider YECHA Infocard EC number 831 Admelin referencer Ketch Ipubchem Sider text number Kuunidermd YUN number Urkumtux dashboard EPA Tisidinchian Chisipik Tush Ike BZHJM EDXRYG GRVUH FFFAOYS A Inyianchiakaktushi BZHJM EDXRYG GRV Afayas Miles Property Chemical Formulatic Muller Mass Mol Apier and Checolorless Gasidor Police Intensity Melting Point CF 119.3 K Boiling Point C 7.9 F 259.8 K solubility in Watergl 0.0432 mol vapor pressure of mercury 20 C68 F magnetic susceptibility mol thermochemistry head capacity C 0.8592 gas 0.9504 solids enthalpy affirmation kernel solid hazard labeling pictogram signal Wardangerizard statements precautionary statements Perf 704 Fire Diamond Flash Point CF 212K Explosive Limits or Percentage NEOS US Health Exposure Limits IPEL Permissible TWA1C5 REL Recommended Chital Immediate Danger except where otherwise noted. Data are given for materials in their standard state at 25C 100 PY. Verify what is YN. Info box reference a chemical compound. Uses Vinyl chloride, also called vinyl chloride monomer VCM, is exclusively used as a precursor to PVC. Due to its hazardous nature, VCM is not found in other products. Polyvinyl chloride PVC is very stable, storable, and not toxic. Until 1974, vinyl chloride was used in aerosol spray propellant. Vinyl chloride was briefly used as an inhalational anesthetic, in a similar vein to ethyl chloride, though its toxicity forced this practice to be abandoned. Smaller amounts of vinyl chloride are used in furniture and automobile upholstery, wall coverings, housewares, and automotive parts. Vinyl chloride has also been used in the past as a refrigerant. Production. Vinyl chloride was first produced in 1835 by Justus von Liebig and his student Henry Victor Regnault. They obtained it by treating 12-dichlorophene with a solution of potassium hydroxide and ethanol in 1912. Fritz Klatt, a German chemist working for Grisham Electron, patented a means to produce vinyl chloride from acetylene and hydrogen chloride using mercuric chloride as a catalyst. This method was widely used during the ERS and ERS in the West. It has since been superseded by more economical processes based on ethylene in the United States and Europe. The mercury-based technology is the main production method in China. Approximately 31.1 million tons were produced in 2000. Two methods are employed: the hydrochlorination of acetylene and the dihydrochlorination of ethylene dichloride 12-dichlorophene. Numerous attempts have been made to convert ethane directly to vinyl chloride. Gold and platinum-based catalysts have been proposed as replacements for mercury 12-dichlorophene, also known as ethylene dichloride, EDC, can be prepared by halogenation of ethane or ethylene, inexpensive starting materials. EDC thermally converts vinyl chloride and anhydrous. This production method became the major route to vinyl chloride since the late Churchill. Thermal cracking reaction is highly endothermic and is generally carried out in a fired heater. Even though residence time and temperature are carefully controlled, it produces significant quantities of chlorinated hydrocarbon side products. In practice, the yield for EDC conversion is relatively low, 50 to 60%. The furnace effluent is immediately quenched with cold EDC to minimize undesirable side reactions. The resulting vapor-liquid mixture then goes to a purification system. Some processes use an absorber stripper system to separate from the chlorinated hydrocarbons, while other processes use a refrigerated continuous distillation system. Acetylene reacts with anhydrous hydrogen chloride gas over a mercuric chloride catalyst to give vinyl chloride. The Churchill reaction is exothermic and highly selective. Product purity and yields are generally very high. This route to vinyl chloride was common before ethylene became widely distributed. When vinyl chloride producers shifted to using the thermal cracking of EDC described above, some used byproduct in conjunction with a collocate acetylene-based unit. The hazards of storing and shipping acetylene meant that the vinyl chloride facility needed to be located very close to the acetylene generating facility. China still uses this method to produce vinyl chloride due to the large reserves of coal from which acetylene is produced. Ethane is readily available, particularly on the U.S. Gulf Coast. Ethylene is made from ethane by cracking ethane, and then ethylene is used for production of vinyl chloride. Hence, to save the processing cost for manufacturing ethylene, numerous attempts have been made to convert ethane directly to vinyl chloride. A direct feed of ethane to vinyl chloride plants could thus considerably decrease the raw material costs and make the plants less dependent on cracker capacity. The conversion of ethane to vinyl chloride can be performed by various routes: high temperature chlorination to 3, high temperature oxychlorination to high temperature oxidative chlorination to 3. Major drawback to the use of ethane are the forcing conditions required for its use, which can be attributed to its lack of molecular functionality. In contrast to ethylene, which easily undergoes chlorine addition, ethane must first be functionalized by substitution reactions, which gives rise to a variety of consecutive and side chain reactions. The reaction must, therefore, be kinetically controlled in order to obtain a maximal vinyl chloride yield. Vinyl chloride yields average percentage per pass. Ethylene, ethyl chloride, and 12-dichlorothin are obtained as major byproducts. With special catalysts and at optimized conditions, ethane conversions of greater than % have been reported from oxychlorination reactions. That ethylene formed can either be recycled or oxychlorinated and cracked in a conventional manner. Many such ethane-based processes have been and are being developed. Storage and transportation. Vinyl chloride is stored as a liquid. The presently accepted upper limit of safety as a health hazard is 500. Often, the storage containers for the product vinyl chloride are high-capacity spheres. The spheres have an inside sphere and an outside sphere. Several inches of empty space separate the inside sphere from the outside sphere. This void area between the spheres is purged with an inert gas such as nitrogen. As the nitrogen purged gas exits the void space, it passes through an analyzer that is designed to detect if any vinyl chloride is leaking from the internal sphere. If vinyl chloride starts to leak from the internal sphere, or if a fire is detected on the outside of the sphere, then the contents of the sphere are automatically dumped into an emergency underground storage container. Containers used for handling vinyl chloride at atmospheric temperature are always under pressure. Inhibited vinyl chloride may be stored at normal atmospheric conditions in suitable pressure vessel. Uninhibited vinyl chloride may be stored either under refrigeration or at normal atmospheric temperature in the absence of air or sunlight, but only for a duration of a few days. If for longer periods, regular checks should be made for the presence of polymers. Transporting VCM presents the same risks as transporting other flammable gases such as propane, butane, LPG, or natural gas, for which the same safety regulations apply. The equipment used for VCM transport is specially designed to be impact and corrosion resistant. Fire and explosion hazard. In the U.S., OSHA lists vinyl chloride as a Class I flammable liquid with a National Fire Protection Association flammability rating of 4. Because of its low boiling point, liquid VCM will undergo flash evaporation, i.e., auto-refrigerate upon its release to atmospheric pressure. The portion vaporized will form a dense cloud more than twice as heavy as the surrounding air. The risk of subsequent explosion or fire is significant. According to OSHA, the flash point of vinyl chloride is CF. Its flammable limits in air are lower 3.6 volume percentage and upper 33 volume percentage. The explosive limits are lower percentage, upper percentage by volume in air. Fire may release toxic hydrogen chloride and carbon monoxide CO. VCM can polymerize rapidly due to heating and under the influence of air, light, and contact with a catalyst, strong oxidizers, and metals such as copper and aluminium with fire or explosion hazard. As a gas mixed with air, VCM is a fire and explosion hazard. On standing, VCM can form peroxides, which may then explode. VCM will react with iron and steel in the presence of moisture. Health effects. Vinyl chloride finds its major application in the production of PVC. It is volatile, so the primary exposure is via inhalation, as opposed to the consumption of contaminated food or water, with occupational hazards being highest. Prior to 1974, workers were commonly exposed to 1,000 vinyl chloride, causing vinyl chloride illness such as acrostolysis and Raynaud's phenomenon. The symptoms of vinyl chloride exposure are classified by levels in ambient air, with 4,000 having a threshold effect. The intensity of symptoms varies from acute, including dizziness, nausea, visual disturbances, headache, and ataxia, to chronic above 12,000, including narcotic effect, cardiac arrhythmias, and fatal respiratory failure. RADS reactive airway dysfunction syndrome may be caused by acute exposure to vinyl chloride. Vinyl chloride is a mutagen having clastogenic effects which affect lymphocyte chromosomal structure. Vinyl chloride is a group 1 human carcinogen posing elevated risks of rare angiosarcoma, brain and lung tumors, and malignant hematopoietic lymphatic tumors. Chronic exposure leads to common forms of respiratory failure, emphysema, pulmonary fibrosis, and focused hepatotoxicity, hepatomegaly, hepatic fibrosis. Continuous exposure can cause CNS depression, including euphoria and disorientation. Decreased male libido, miscarriage, and birth defects are known major reproductive defects associated with vinyl chloride. Vinyl chloride can have acute dermal and ocular effects. Dermal exposure effects are thickening of skin, edema, decreased elasticity, local frostbites, blistering, and irritation. The complete loss of skin elasticity expresses itself in Raynaud's phenomenon. And hepatotoxicity of vinyl chloride has long been established since the years when the PVC industry was just in its infant stages. In the very first study about the dangers of vinyl chloride, published by Patty in 1930, it was disclosed that exposure of test animals to just a single short-term high dose of vinyl chloride caused liver damage. In 1949, a Russian publication discussed the finding that vinyl chloride caused liver injury among workers. In 1954, B.F. Goodrich Chemicals stated that vinyl chloride caused liver injury upon short-term exposures. Almost nothing was known about its long-term effects. They also recommended long-term animal toxicology studies. The study noted that if a chemical did justify the cost of testing and its ill effects on workers and the public were known, the chemical should not be made. In 1963, research paid for in part by Allied Chemical found liver damage in test animals from exposures below 500 parts per million. Also in 1963, a Romanian researcher published findings of liver disease in vinyl chloride workers. In 1968, Muchler and Kramer, two Dow researchers, reported their finding that exposures as low as 300 caused liver damage in vinyl chloride workers, thus confirming earlier animal data in humans. In a 1969 presentation given in Japan, P.L. Viola, a European researcher working for the European vinyl chloride industry, indicated every monomer used in VC manufacture is hazardous. Various changes were found in bone and liver, particularly much more attention should be drawn to liver changes. The findings in rats at the concentration of 4 to 10 are shown in pictures. In light of the finding of liver damage in rats from just vinyl chloride exposure, Viola added that he should like some precautions to be taken in the manufacturing plants polymerizing vinyl chloride, such as a reduction of the threshold limit value of monomer. In 1970, Viola reported that test animals exposed to 30,000 vinyl chloride developed cancerous tumors. Viola began his research looking for the cause of liver and bone injuries found in vinyl chloride workers. Viola's findings in 1970 were a red flag to B. F. Goodrich and the industry. In 1972, Maltini, another Italian researcher for the European vinyl chloride industry, found liver tumors including angiosarcoma from vinyl chloride exposures as low as 250 for 4 hours a day. In 1997, the U.S. Centers for Disease Control and Prevention (CDC) concluded that the development and acceptance by the PVC industry of a closed-loop polymerization process in the late ERS almost completely eliminated worker exposures, and that new cases of hepatic angiosarcoma in vinyl chloride polymerization workers have been virtually eliminated. Houston Chronicle claimed in 1998 that the vinyl industry manipulated vinyl chloride studies to avoid liability for worker exposure and extensive and severe chemical spills in local communities. According to the EPA, vinyl chloride emissions from polyvinyl chloride PVC, ethylene dichloride EDC, and vinyl chloride monomer VCM plants cause or contribute to air pollution that may reasonably be anticipated to result in an increase in mortality or an increase in serious irreversible or incapacitating reversible illness. Vinyl chloride is a known human carcinogen that causes a rare cancer of the liver. EBA's 2001 updated toxicological profile and summary health assessment for VCM in its integrated risk information system IRIS database lowers EPA's previous risk factor estimate by a factor of 20 and concludes that because of the consistent evidence for liver cancer in all the studies and the weaker association for other sites, it is concluded that the liver is the most sensitive site, and protection against liver cancer will protect against possible cancer induction in other tissues. Microbial remediation. The bacteria species Nitrosamines europaea can degrade a variety of halogenated compounds, including trichlorophyllene and vinyl chloride. Further reading. Medicine, The Plastic Peril, time, May 13, 1974, archived from the original on June 12, 2007, retrieved to July 2010.